For number 3 from Friday's packet, we have two masses hanging on a pulley, and we want to find the acceleration of the block. So I'm going to draw a free body diagram for each of these. So I've got the 2m block, and I've got the m block, both of which will have a force of gravity. This guy's force of gravity will just be mg. This one will be a bigger force of gravity. It'll be 2mg. And it's still mass times gravity, it's just that this guy has a mass of 2m. Right, and then both of them have tension pushing up or pulling it up. There's no normal force because there's no surface pushing up on it. It is just the weight and the tension force. The tension force is going to be the same for each one because this is the same rope between them, so it has to be the same. All right, now that we have our free body diagrams, we're going to write our net force equation. So this one, this object is going to accelerate down. This one is going to accelerate up because they're physically connected, so they can't both go down. So this one is going to be the bigger force minus the smaller force, 2mg minus tension, and then this will still be the bigger force minus the smaller force. Here the bigger force is up because it's accelerating up, so this one will be tension minus mg. All right, and then we know that the net force is always the mass times the acceleration, so here that is just ma equals t minus mg. And for here, the mass is 2m, so it's 2ma equals 2mg minus tension. Okay, now I have two equations. I'm looking for the acceleration, and I can leave it in terms of g, but I can't have tension in my answer, so what I want to do is I want to solve for tension right here. I'm going to rewrite this over here. So this is ma equals t minus mg. So then I'm going to add the mg over. I have ma plus mg equals tension. And now that I have tension, I can substitute that in for the t right here. So 2ma equals 2mg minus tension. So minus the ma plus the mg. One mistake that's really easy to make right here is to not distribute your negative sign. But you need to because you're subtracting tension, all of tension, so you're subtracting the ma and you're subtracting the mg. So then this becomes minus ma minus mg, and now we're just combining like terms. So I'm going to add the ma over to the other side. That's going to give me 3ma. And then I have 2mg minus mg, so that's just mg, just like 2x minus x would leave you with just 1x. The m's cancel out, and then to get acceleration, you just divide by 3, so this is g over 3. Number 4, a block of mass m is, oh wait, we did number 4 in class, I'm going to redo this. Number 5, we have a person of mass m stands on a scale in an elevator. For each question, we are choosing between these for what the scale would read when it's doing certain things. So I'm going to first start by drawing a free body diagram. So this is the person on the elevator. One force, obviously, is the force of gravity. Their weight, mg. I'll just put mg. And then the other force is the normal force, pointing up. Now, if they're at rest, these two are equal to each other. If it's accelerating up, so let's make a note right here, if the elevator, the person is accelerating upwards, that means that Fn is greater than the force of gravity because you have a bigger force up. If the acceleration is downwards, so if it's accelerating downwards, it's tempting to be like, oh, that means Fg is bigger, which is true. Fg will be bigger than Fn, but it's not that Fg, your weight, all of a sudden became a lot heavier. Fg actually stayed the same, you just have Fn is smaller. So then Fg is greater, which really just means that Fn is less than the weight. Right? So then in each of these situations, we basically just need to figure out which way is it accelerating. So, oh, by the way, it says, what does the scale read? The scale is going to read the normal force. So I'm figuring out basically if the normal force is more or less or equal to the weight in each of these situations. If the elevator is moving upwards with decreasing speed, so decreasing speed means it's getting slower. Moving upwards means the velocity is upwards. So if you are decreasing speed, getting slower, no matter what, that means your velocity and your acceleration are in opposite directions. So if my velocity is upwards, then my acceleration must be downwards if it's decreasing in speed. So that means if your acceleration is down, that means your net force is down, which is why, in this case, if your net force is down, that means Fg is a greater force than Fn, which means Fn, this scale would read less than Fg, so between A between 0 and mg. Which is what we said right here. If acceleration is down, that means Fg is the greater force, which means that Fn is less than the weight. So the scale Fn would read between 0 and the weight mg. Right? What about if the elevator is moving down, not up? So the elevator is moving down, which means velocity would be down. And then the decreasing speed means acceleration is in the opposite direction, because it's going to oppose if it's decreasing in speed or getting slower. If your velocity is down and then slowing down, acceleration must be up, which means your net force must be directed up. If you have a bigger, if your net force is up, that means the up force is bigger, which means Fn is greater than the weight, which means that the weight, or the scale, would read more than the weight, C. Which is again what we said right here. If acceleration is up, then normal force would be the greater force, so it would be more than mg. If the scale, or if the elevator is moving up and it's getting faster, if it's getting faster, then that means that your acceleration is in the same direction, so then your acceleration is up, which means net force is up, which we already decided would be situation C. If the elevator is moving down and increasing in speed, getting faster, acceleration is in the same direction, so acceleration would be down, that's a net force down, which would be situation A. Again, we kind of described these over on the side. Now, if it's moving at a constant speed, it doesn't matter which way it's moving. If it's at a constant speed, that means your net force is 0, your forces are balanced, which means your Fn would just be equal to your weight. So your scale would just read the weight B. For both of these, because moving down, moving up, moving to the left, or at rest, if they're at constant speed, or at rest, would all mean balanced forces, so these two would have to be equal. Right, number 6, a box is moving north with a constant, or at a constant velocity of 5. As soon as you see constant velocity, if we're talking about forces, you should think and maybe even write out balanced forces. Balanced forces. All right, it says the box has a force of 3 newtons to the east. It has a force of 3 newtons to the north, and it only has one other force. What must be true about the magnitude and direction of the one other force acting on the box? So let's just think direction right now. I have choices between southwest, so it could be something like this, or northeast, which would be something like this, or just straight west. So the idea with constant velocity is, again, your forces are balanced. So if you have north and east, then you need to counterbalance that with a south and a west force. So I'm going to cross off D and E, because northeast would just mean that it's, in addition to this east and this north force, you would have an acceleration, a net force northeast. If you just have west, then the east-west balance out, but then you would have an acceleration or a net force north. So those don't make sense. So everyone should probably have gotten that pretty easily, just the direction. Now we need to know about the magnitude. So this force right here, is it exactly 3 newtons? Is it more than 3 newtons? Is it less than 3 newtons? Remember, the idea is that you need this 3 newtons north to be balanced by 3 newtons south. You need this 3 newtons to the east to be balanced with 3 newtons west. Now this is together one force. The east, or the south and the west make one force. So if just this y part of the force is 3 newtons, and if just this x part of the force is 3 newtons, that means that the total force, the two parts together, have to be more than 3 newtons. And then it's asking you to solve for the actual magnitude of that force. Let's think about if I need to go down 3 newtons, or south 3 newtons, and east 3 newtons, then together, hopefully you see a right triangle right now, and you're thinking, Pythagorean theorem, to find the total force that is in this angle direction, you just use Pythagorean theorem. B squared plus 3 squared would get you your missing force squared. That's 9 plus 9, so force would be the square root of 18. You can leave it like that. You can put it in your calculator. It doesn't matter. AP test is kind of similar to the ACT, where often they leave it in the square root instead of rounding the fractions, or sorry, rounding to the decimals. You also might see it where you like have the simplified radical. So here, technically 18 would be like 9 times 2, and 9 is a perfect square, so it would come out as a 3. But if you're in the multiple choice and you're like, crap, I don't remember how to do this, you can just type 3 root 2 in your calculator and make sure you get the same answer as root 18, same decimal. All right, number 7, when you are walking on the ground, the force that pushes you forward. So it might be tempting to say the normal force, but remember the normal force is only going to, it's perpendicular to the surface, so the normal force can actually only push you straight up, and when you're walking, you're definitely going more than just straight up. You're going forward to like the side in this diagram. The force that pushes you forward is actually the force of friction. Which hopefully makes sense, because if the ground is super slippery, right, you don't get to move. Your shoe is pushing against like the fibers in the carpet or whatever the surface is, going against. If there was no friction, it would just slide and you would not move forward. Second part is which type of friction. Is it static or kinetic friction? It's tempting to say kinetic friction because you are moving, but if you think about your shoe on the surface, your shoe isn't sliding across the surface, it's just moving forward, so it's actually static friction. This next part is very poorly worded, but what I was trying to go here is the force that pushes you forward compared to the force that you push on the ground. I was trying to say like those are the same force, so how much you push on the ground compared to how much the ground pushes on you is the same, because equal and opposite, the same two objects on each other. All right, number 8, so we have an object that's moving with an initial velocity as shown, and then a force is exerted on the object in the direction shown, and we want to know which object is increasing in speed while changing directions at that instant. So if it's moving to the right and just now a force is applied at that instant, we want it increasing speed and changing directions. So I'm going to start with I'm going to call these A, B, and C, and D, so that's just easy to match. We'll go here. So the object that is increasing in speed, so getting faster, well, it's only going to get faster if the acceleration's in the same direction as the velocity, which means acceleration here is provided by the force. So if my force is in the same direction of the velocity. But it's also changing directions, so the answer here was D, because see how you have a force that's adding, it's also to the right in the direction of velocity, but then it's also adding in a force or an acceleration upwards. So it would be going to the right, and now as soon as this force is applied, it's going to get faster to the right, and it's also going to start moving upwards. So this one was D. The one that is decreasing in speed while also changing directions, that would be C right here. Because see how your force is against this velocity, so your acceleration, you have an acceleration up, which could still be, at this instant, it's moving down, beginning slower, and then starts to also move to the right. The object that is increasing in speed but not changing directions, that would be B, because your force is in the same direction as your velocity, so it just gets faster down. And then the one that's decreasing in speed but not changing directions, that would be A. Now if you're like, wait, but that's going to make it stop and go the other way. That is true, but that's not going to happen instantaneously. Before it stops, right, you need the force to slow it down to 0 and then start going the negative direction. So it wouldn't be changing directions at that instant. All right, number 9, we've got 3 boxes stacked on top of one another in an elevator, and we want to, oh gosh, lots of different forces, rank the forces from largest to smallest. So first, let's decide which of these forces are equal to each other. So for number 9, it says the force of the 3 on the 2. So I'm going to call that F3 on 2. And then P is the force of 2 on 3. So that's the force of 3 on 2. Now, by Newton's third law's definition, those have to be equal because it is the same 2 objects on one another. 3 on 2 and 2 on 3, they exert the same force on each other no matter what's happening. If the elevator is accelerating up, down, if it's at rest, if it's at constant velocity, those will always be equal. Right, the force of the 3 kilogram on the 1 kilogram and the 1 on the 3, so these actually do not exist because they are not in contact. with each other. The 3 cannot exert a force on the 1 kilogram box if they aren't touching. So that was a trick. Those don't exist. The force of the 2 on the 1, for sure, these 2 exist. They are touching each other. They will have a force on each other. So 2 on 1 and 1 on 2. Those are, again, the same 2 objects on each other, so those will be equal to each other. And then the 1 and the floor aren't in contact with each other, so they will have a force. So the floor and 1 in the floor. Those will, again, be equal. So basically, I have 3 different pairs of forces. These 3 different pairs of forces will not be the same force. Most of you probably can just look at this and be like, how much the floor is pushing up on the 1 compared to how much the 1 is pushing up on the 2 compared to how much the 2 is pushing up on the 3. Well, the floor is holding up all of that weight, so it's going to be pushing up more than the 2 kilogram, which is only holding up like the 3 kilogram, etc. But it helps to just draw the free body diagram. So before I do my ranking, I'm going to draw my free body diagram for each. So for my 3 kilogram, I've obviously got the force of gravity pointing straight down, and I'm just going to calculate force of gravity is mass times gravity. We'll just use 10 as gravity, so that would be 30 newtons. And then I have the force of the 2 kilogram, the 2 pushing up on the 3, so I'll just call that F23. Now the next one, that will be the 2 kilogram. Of course, we have the weight of the 2 kilogram, which would just be 20, 2 times acceleration of gravity, 10. And then we also have another force pointing down. We have the force of this box pushing down on the 2 kilogram, which is just the force of box 3 on 2. Right, and then we have the force that's holding up box 2, so that would be the 1 kilogram on the 2 kilogram. So the force of the 1 on the 2, technically these are like normal forces because it's the surface holding up another or pushing up on another one. And then lastly, we've got the 1 kilogram, which of course we have the weight, which is 10. And then the 1 kilogram doesn't just have its own weight, it also has the box of the force from the 2 kilogram box pushing down on it. So that is the force of the 2 on the 1 pushing down on it. And what's pushing up on the 1 kilogram is the force of the floor. Okay, now it said right now the elevator is at rest. That makes this really easy because these are all balanced forces. So this is Fg, this would be 30. We know the force of 2 on 3 has to be equal to the force of 3 on 2, so then this is 30 as well. Well, if this is balanced, if you have 20 plus the 30 kilograms from the box pushing down on it, now that means that the amount 1 is pushing up on 2 is 50 kilograms. Here we've of course got the weight, or sorry, I forgot to say 1 to 2 is equal to 2 on 1, so this would also be 50. And then when you add these 2 together, that's balanced with the upward force, which is 60 newtons. So now it's really easy to rank them because the force of the floor on the first box is 60 kilograms. Between the 2 and the 1 is 50. Between the 2 and the 3 is 30 kilograms. So from largest to smallest, that would be the floor on 1, which is equal to 1 on the floor. And then after that would be, or the next biggest would be between the 2 and the 1. So 2 and the 1 and 1 on 2. And then the smallest would be the 2 on 3 and the 3 on 2. Now if we assume the elevator is moving upwards at an increasing speed, so that would be moving up, velocity up. Increasing speed means acceleration is in the same direction, so that would be an acceleration up. If there's an acceleration up, this is not 30 newtons anymore. It's more than 30 newtons. And then these 2, whatever they are, because this is now more than 30, they have to add up. This one will be even more than that. And then this, of course, is bigger because that force is bigger. These 2 have to add up to even more than that, but our ranking actually hasn't changed. So this is still the same because no matter what, these 2 have to equal each other, these 2 have to equal each other, these 2 have to equal each other. And if the boxes are accelerating, well, now this is more than holding up all of the weight. It's more than the 60. This is more than holding up the weight of the 2, the 50. This is more than holding it up. But this is still holding up all of the weight plus the acceleration. This is holding up some of the weight plus the acceleration, and then only one box weight plus the acceleration, so the rankings still stand. But but the balanced forces do not still stand anymore. These would be greater forces up than the down forces. All right, number 10, what would happen to the normal force if the angle were increased or decreased, etc.? So I'm going to draw a like super steep one, mass, and then I'm going to draw a super, super flat one, like this. So here, the normal force is almost, as soon as it's flat, now your normal force is just equal to the gravitational force. As you increase the angle, you get a smaller and a smaller normal force because the portion, or I guess the component of the weight across from the normal force is the mg cosine. So the bigger and bigger your angle gets, the smaller and smaller that cosine of the angle gets. So if the angle is increased, you get a much smaller normal force. If the angle is decreased, you get a bigger normal force until it is just equal to the weight when it's flat. What happens to the acceleration of the block? Well, the acceleration is like the part that is not balanced out, the part of the gravity force that is not balanced out by the normal force. So the steeper I get, the more the net force, which is just your like component that's not held up by the normal, the mg sine of the angle, the greater that's going to get. So the greater the angle, the more the acceleration, and then the smaller the angle, the less the acceleration. Which makes sense that these are opposite because, right, we have a greater acceleration because the normal force, the ramp, is holding it up less. It's allowed to just fall freely more. Number 12, which of the following is true about the sign, the tensions from this hanging sign? So I drew a free body diagram right here at that point. So I've got tension, and I've got this tension too, and I've got T1 that's like at a higher angle, something like this. All right, now I'm going to break this down because these two are angles, so I'm just going to call like T1y and T1x. And then T1y, T2x, and T2y. And then T3. These are not to scale, I just started kind of drawing them slightly exaggerated. So this wasn't to scale, I'm just breaking down these parts, these two into their XY parts. So part A is saying the tension in T3 is equal to the weight of the sign. So let's look at this part right here. That makes sense because T3 is just, if this is at rest, right, it's just holding up this sign. It's not accelerating at all, so this tension is just the weight of the sign. That makes sense. A is true. We're choosing all that apply. B, the tension in 1 is greater than the tension in 2. So if we look right here, we can say that the x component of y is equal to the x component of 2, but they're at different angles, so that tells me that they have different tensions. Because their x parts have to be equal and their angles are different, so their actual total forces of the tensions have to be different as well. Now we're just thinking through, okay, so is it true that T1 is the greater force? So how I like to think about it is I'm going to look and say, like, okay, T1 is mostly pulling up. It's only pulling to the side a very, very little bit. T2 is mostly pulling to the side. It's not pulling up quite as much. So if this guy's x component is equal to this guy's x component, when this force is mainly to the side, that means that this T1 must be a really, 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 really strong force, because at such a small, like, angle, or I guess big angle, I don't know, such a vertical angle, to have a big x component that will balance out this guy's x component, this must be stronger tension. So yes, B was also true. C, the x component of the tension in T2 is greater than the x component of the tension in T1. No, that's not true at all. Their x components have to be balanced. They have to equal out because it's only those two that would be in the x direction, and the net force is 0. So that's not true. The y component in the tension is equal to the y component in 2 is equal to the y component in 1. No, that's not necessarily true. In fact, T1 is going to hold up more of the weight than T2 will, because it is a stronger tension and it's at a bigger angle or higher angle. These two add up to the T3, but they are not the same. So only A and B. Number 13, a force F pulls on a box of mass M at an angle of phi. When the angle is halved, what happens to the normal force and the acceleration? So kind of similar to what we're doing on the incline plane. Here I'm going to draw a free body diagram just because it helps. So right here, we've of course got the force of gravity and we have a normal force. Now, my normal force does not necessarily equal my force of gravity here because I also have this pulling force up. So I'm going to break this pulling force up into Fy and Fx. It doesn't say that there's friction or not. I'm going to ignore friction for right now. That was my bad. I read this question. I didn't say, but I think I meant for it to be frictionless. It doesn't change your answer, but it does make it slightly more simple. So we'll just ignore friction for now. I want to know what's going to happen to the normal force and the acceleration if I decrease my angle. So if I half my angle, that means that I have more x force and I have less y force because my angle is more to the side than up, whereas before it was more up than to the side. So if we think about, let's start with just the normal force. We know that the normal plus Fy equals Fg. So normal plus Fy will equal Fg. Well, the Fg of this box has stayed the exact same. That certainly has not changed because I haven't changed the mass or the acceleration of gravity. But now this is smaller. So if this is smaller, but they still add up to hold up the same weight, then that means the normal force must be pushing up more than before. So we know the normal force is going to increase. And then we're thinking about the acceleration of the block. Well, the acceleration comes from this force right here, right? These are going to balance out whether the normal force will have to push up more or less to compensate. These are going to balance out. This one does not have something to balance out. This is your net force, which is causing the acceleration sideways. So if I have a smaller angle, I now have a greater net force to the side, so I'm going to have a greater acceleration than before, B. Number 14, a force of 50 newtons pulls 3 blocks of masses 20, 10, and 5 respectively. So 20 kilograms, 10 kilograms, 5. Find the tension in each of the ropes. So I'm going to redraw. This is 20 kilograms. I'm going to call this tension A. This is 10 kilograms. This has tension B and tension A pulling the opposite direction. And then this is 5 kilograms. It's got the tension C and the tension B, the opposite direction. Now it says that a force of 50 newtons is pulling this guy right here. So I already know that tension C is just that applied force, 50 newtons. Now I'm going to go through, I'm going to write my net force equation. So this one's easy. Your net force is just tension A. This one, my net force, because it's going to accelerate to the right, I'm going to say right minus left, because this is a bigger force minus a smaller force. And then, I keep doing my F's like a T. So the net force for the 5 kilogram is going to be the 50 minus tension B. Now net force, these do not all have the same net force. They have the same acceleration because they're physically connected, but they have different masses. So I'm just going to replace my net force with mass times acceleration. So 10A and then 5A. Okay. So I can go ahead and substitute in 20A for tension in A. So I have 10A equals TB minus 20A. Add that over, I have 30A equals TB. I can now substitute that in for TB. So 5A equals 50 minus TB, which we just said was 30A. Add that over, 35A equals 50. Divide. I think that's 1.4 something. 50 over 35. Yep, this gives me an acceleration of 1.43 for my answer. And then now I'm not done because I actually wanted these tensions, but it's really easy because I can just say, okay, 20 times that, that's going to give me a tension of 28.57 newtons for A. Tension in B is 30 times the acceleration, so that's going to give me a tension of 42.86 newtons. And then the other one was already given to me, T3 was 50. For number 15, a homeowner pushes a lawnmower across a horizontal patch of grass with a constant speed. So as soon as you see constant speed, you're thinking balanced forces. right? I have kind of a funky free body diagram. I'm gonna redraw this. So I've got my weight right here. I've got my normal force. I'm gonna have to pause the video.